so far we have not taken into account any internal structure of the particles that constitute our perfect gas. We have assumed these to be structureless. We've considered the kinetic, the translational degrees of freedom, particles that can move in space, but we have not taken into account any internal dynamics. Now, in many real gases, we have molecules, and molecules have a structure. They can rotate, they have a moment of inertia, they can vibrate, and all of this is yet to be taken into account. As a starting point to treat this mathematically, I would like to consider the canonical partition function, not as we have done often the grand canonical, but here I would like to start with the canonical partition function. So this is the situation where we have the particle number given as a sharp constraint. So we know for sure the number of particles in our gas. The idea is to say that the translational degrees of freedom, the motion of these particles in space, decouples and is independent of the internal dynamics of the particles. The vibrations, rotations, and whatever you can have internally. This means mathematically you can treat that in two distinct Hilbert spaces. You have a Hilbert space for the dynamics in space, and we have a Hilbert space to describe the internal dynamics, and respective Hamiltonians. One Hamiltonian to describe the internal dynamics, another Hamiltonian to describe the free motion in space. There's no interaction between the two, and this implies that when we calculate the partition function, the partition function factorizes. We can consider a canonical partition function that describes only, and that we calculate only with the, or that describes only the translational dynamics, and that does not take into account the internal structure, so that we can calculate with the Hamiltonian for the free motion in space. This is the partition function that we have always considered so far, because we have neglected any internal dynamics. So this is the canonical partition function for a gas composed of structureless particles. Such a gas is also called a monatomic gas. So this is a gas composed of structureless particles, and this is what we have considered so far. This depends on beta, particle number, and volume, as before. And then we have the internal degrees of freedom, the internal dynamics, which is decoupled from the translational dynamics, described by some internal Hamiltonian, and associated with this internal dynamics is an internal partition function. Now, the internal dynamics of the individual particles in the gas, or the molecules in the gas, are independent from each other. So if I have two molecules, gas molecules, the internal dynamics of the first gas molecule is unaffected and independent of the internal dynamics of the other gas molecule. So here we can factorize again, and we can say the partition function of the internal dynamics of all the molecules is the partition function of the internal dynamics of an individual molecule to the power n. Because we have n identical and independent molecules. Now the monatomic part and the internal part, the monatomic partition function and the internal partition function, are simply multiplied to get the partition function of the complete system. So due to this independence, the full partition function factorizes. This partition function relates to the internal dynamics, which may be rotations, oscillations, and so on. This holds for the canonical partition function, but of course at the end of the day we've used the grand canonical partition function with so much success that we would like to go back to the grand canonical partition function. And you may remember that we can obtain the grand canonical partition function from the canonical partition function by a discrete Laplace transform. So the grand canonical partition function as a function of beta, alpha, and volume, that's this discrete Laplace transform. It's the sum from n over n from 0 to infinity, e to the power alpha times n, and then times the canonical partition function as a function of beta, particle number, and volume. We can insert our result from the first line. We can say this is the sum n going from 0 to infinity, e to the power alpha n. Let me write this internal partition function first. It's a function of beta to the power n. And then we have the canonical partition function of the monatomic gas as a function of beta, particle number, and volume. Now these two factors, e to the power alpha n and the nth power of the internal partition function, we can write as a single exponential. We can write it as e to the power alpha plus the log of the internal partition function of beta times n. So when you look at this formula, it just looks like the discrete Laplace transform of the canonical partition function of a monatomic gas, only with the Lagrange parameter alpha replaced by alpha plus the log of the internal partition function. You can say that the grand canonical partition function, the full grand canonical partition function that takes into account the internal dynamics as a function of beta, alpha, and volume, is equal to the discrete Laplace transform of the canonical partition function of a monatomic gas with, rather than alpha, alpha plus the log of the internal partition function. And this discrete Laplace transform gives the grand canonical partition function of the monatomic gas at inverse temperature beta, then Lagrange parameter alpha plus log of the internal partition function and volume. So you see that the way that you account for internal dynamics of the molecules in a gas is you take the grand canonical partition function of a structureless gas, of a monatomic gas. This is a function of beta, alpha, and volume. And all you have to do is that you have to replace the alpha by alpha plus the log of the internal partition function. And that's where the internal dynamics comes into play. In this equation, we can finally take on both sides the logarithm. Now, for the logarithm of the grand canonical partition function of a monatomic gas, we have a formula, at least in the classical limit. So let's look at the classical limit. In the classical limit, we found that the log of the grand canonical partition function of a monatomic gas goes like e to the alpha, but now we have to replace alpha by alpha plus the log of the internal partition function times volume times beta to the power minus 3/2. So in this classical limit on the right hand side, you have e to the log of the internal partition function, and this of course simply gives the internal partition function. So you find at the end that the log of the full grand canonical partition function of a gas with internal structure is given by the internal partition function of the molecules times, well, and all that remains then is the e to the alpha times volume times beta to the minus 3/2, which is once again the ordinary grand canonical partition function of a structureless gas in the classical limit, or the log of that. So this is the log of the grand canonical partition function of a monatomic gas as a function of beta, alpha, and volume. So to conclude this calculation, what we find is that in terms of the log of the grand canonical partition function, when we want to include internal structure, all we have to do is multiply with the partition function of the internal dynamics of a single molecule. So at the end of the day, it's a very simple way, very straightforward way of incorporating the effects of internal dynamics. So now we have a general framework that allows us to incorporate internal dynamics into the description of gases. And I'd like to put this into practice in two cases. One case is the diatomic molecule. So the gas is now composed no longer of structureless atoms, but it's composed of a molecule, and the molecule consists of two atoms. That's why it's called diatomic. And the other application will be the discussion of dilute solutions. That comes afterwards. So a diatomic molecule is composed of two atoms. There's a binding between the two. And this molecule can have two types of internal dynamics. It can rotate, so you have to describe those degrees of freedom with a quantum mechanical rotor. So it's a small system. The possible angular momenta are quantized. You have discrete values for the angular momentum. You investigated such a rotor in one of your exercises, your past exercises. So this is one part of the internal dynamics. But then you can also have vibrations of the molecule. I symbolized the binding between the two atoms with an elastic spring. Of course, you will have some different kind of potential between the two atoms. It's just a symbolic representation. But still, as in the case of an elastic spring, you can have vibrations, you can have oscillations, and an elastic spring is often a good first-order approximation of the potential. So to a good approximation, you can describe these vibrational modes as the modes of a one-dimensional harmonic oscillator. Now, rotations and oscillations are independent degrees of freedom, and therefore the internal partition function of such a molecule factorizes. Once again, whenever you have two types of dynamics and they are independent, then each has its associated partition function, and you can factorize. The full partition function is then simply the product of the individual partition functions. So here the partition function that describes the internal dynamics is the product of the partition function of a one-dimensional harmonic oscillator and a partition function of a quantum mechanical rotor. We had discussed the partition function of a one-dimensional harmonic oscillator very early in the semester, and we found that this partition function of the harmonic oscillator is 1 over 2 times the hyperbolic sine of beta h bar omega, where omega is the frequency of this harmonic oscillator, over 2. We shall be particularly interested in the limits of high and low temperature. In these limits, we can approximate this partition function. In the low temperature limit, this is approximately e to the minus beta h bar omega over 2. This is for temperatures where kT is much smaller than the typical energy scale of the harmonic oscillator, which is h bar omega. And it goes to, and it's approximately equal to 1 over beta h bar omega if the temperature, or kT, is much larger than h bar omega. This is the partition function of the oscillator part. For the rotor, you once calculated the partition function on one of the problem sets. That was a slightly more complicated expression. It was an infinite series. You had to sum over all possible eigenvalues of angular momentum. But you also looked at the high and low temperature limits, and there the expression became much simpler. So let me start right away with these two limits for high and low temperature. The partition function of the rotor goes to 1 when kT is much smaller than the typical energy scale of a rotor, and the typical energy scale of a rotor is h bar squared divided by the moment of inertia. And it is approximately 2 times the moment of inertia divided by h bar squared beta for high temperatures when kT is much smaller than this typical scale. Now you derive these limits on your problem set. One specific property of a gas that you can look at and that you can investigate in the laboratory is its specific heat. The specific heat at constant volume, when we considered fluctuations, we found that the specific heat is related to energy fluctuations, and energy fluctuations in turn, or the variance of energy in turn, is related to a second order derivative of the log of the partition function. In this context, we once found that the specific heat at constant volume can be written as 1 over kT squared times the second order partial derivative with respect to beta of the log of the canonical partition function. Now, since the canonical partition function factorizes, it's the canonical partition function of the monatomic structureless gas times the internal partition function. This means that the log of the canonical partition function is the sum of the logs. It's the sum of the, it's a log of the monatomic partition function plus the log of the internal partition function. And this means, when you look at this formula, this means that the specific heat of the full specific heat of the gas is the sum of the specific heats of the monatomic gas and of the internal degrees of freedom. So it's the specific heat of the monatomic gas plus the specific heat associated with the internal degrees of freedom. But this again, you can split up into an oscillation part and a rotation part, because you have another factorization for the internal degrees of freedom. So you can write this as the specific heat associated with the rotational degrees of freedom plus the specific heat associated with the oscillations. For the specific heat of a classical monatomic gas, we know, that's for classical, in the classical approximation only, classically the specific heat of a monatomic gas is 3/2 times Boltzmann constant, 3/2 times K. And this is independent of temperature. For the rotational degrees of freedom, we can study two limiting cases. We can look at low temperatures, Kt much smaller than the characteristic scale of the rotor or much larger than the characteristic scale of the rotor. When the temperature is small, then we know the partition function approaches 1, its log vanishes, and then obviously the partial derivative of the log also vanishes. So the specific heat of the rotor is 0 or approaches 0 for small temperatures. When the temperature is larger than the characteristic scale of the rotor, we know that the partition function of the rotor goes like 1 over beta. So its log goes like minus log of beta. The second order partial derivative of minus log of beta with respect to beta, this goes like 1 over beta squared. And then we have in front of that, in the formula for the specific heat, we have 1 over kT squared. So this is k times beta squared. And we said the second order partial is 1 over beta squared. So the betas cancel. And the specific heat becomes K, the Boltzmann constant. So for high temperatures, the specific heat of the rotor approaches K. Finally, for the harmonic oscillator, again we look at two limiting cases. For low and high temperatures, what happens at low temperature? Look at the formula for the partition function at low temperature. It's this exponential. When you take the log of that, then you simply have the exponent, so that's proportional to beta. You take the second order derivative with respect to beta of beta, and that gives 0. So for low temperatures, the specific heat of the harmonic oscillator approaches 0. For high temperatures, we have the formula below that. It goes like 1 over beta. And then we have the same argument as in the case of the rotor. For the rotor, the partition function also goes like 1 over beta at high temperatures. And we found a specific heat of K. And with the same logic for the harmonic oscillator, we will also find a specific heat K at high temperatures. So we have to the specific heat of a gas composed of diatomic molecules, we have these three contributions. We have the contribution from the translational degrees of freedom. That corresponds to a monatomic gas. And that gives a contribution 3/2 K independent of temperature. Then we have a contribution from the rotational degrees of freedom. That contribution vanishes for low temperatures, and it's K for high temperatures. And finally, we have a contribution from the vibrational degrees of freedom, the oscillations, and there too, the contribution is 0 for low temperatures, and it's K for high temperatures. So we expect that the specific heat of a gas that's composed of diatomic molecules, that changes with temperature. And indeed, a typical behavior that you find when you plot the specific heat divided by Boltzmann's constant as a function of kT, you find that initially at low temperatures the specific heat is 3/2. Then at some temperature, at a typical temperature scale, usually the typical temperature scale or typical energy scale of the rotor is lower than the typical energy scale of the oscillator. So the rotational degrees of freedom kick in first. When you reach the typical energy scale or the typical temperature scale of the rotor, which is h bar squared over theta, then the specific heat of the gas increases and becomes 5/2 times K. And then at an even higher temperature, the typical temperature scale of the harmonic oscillator, h bar omega, then the vibrational degrees of freedom are excited, and the specific heat rises once again to 7/2 times K. So initially you have the translational degrees of freedom only, then the rotational degrees of freedom kick in, and finally the vibrational degrees of freedom kick in. And whenever you reach the characteristic temperature scale of one of the internal degrees of freedom, then the associated specific heat must be added to the specific heat of the gas, and you have this step, you have this increase of specific heat. You can also go the other way. You can come from high temperatures and then lower the temperature, and you can say that first the vibrational degrees of freedom, they freeze. So the at this typical scale, the harmonic oscillator is then practically in its ground state and is frozen, and it no longer contributes to the specific heat. And then you lower the temperature even further, and at some temperature the rotational degrees of freedom freeze. And all the molecules are in the zero angular momentum state and no longer contribute to the specific heat. Yeah? So let me indicate it with this arrow. So when you go in this direction, you can say that as the gas cools down, the internal degrees of freedom freeze. For a typical diatomic gas, room temperature is somewhere in between the typical scale of the rotor and the oscillator. So at room temperature, one is typically in the regime where the rotational degrees of freedom are activated but the vibrational degrees of freedom are not yet activated. So for a diatomic gas at room temperature, you observe a specific heat of 5/2 times Boltzmann's constant. As a final application of our general formulas for the perfect gas with internal structure, let us consider a dilute solution. An example might be a container with a liquid. This is called the solvent. That might be, for example, water. And in this solvent, you have molecules of a dissolved substance. This is called the solute. Yeah, so this is the dissolved substance. Now you could have salt water, and then so the solvent is water, and the solute are the ions of your salt, and they are floating around in the solvent. Now the solute has two types of degrees of freedom. It has translational degrees of freedom, so it can move around in the solvent, and this you can treat to a good approximation as a classical perfect gas, as long as the solution is dilute and the probability is very low that two particles of the solute come close to each other and interact. You can approximately model that as a classical perfect gas. Maybe due to the interaction of the solute with the solvent, the particles of the solute, they carry with them a surrounding because there's some binding with the molecules of the solvent, and so maybe the particles have an effective mass which is different from the free mass of the particles in the solute. But still, then you treat it as an ideal gas with this effective mass. And then in addition to the translational degrees of freedom, there's also some interaction with the solvent. And this is a local interaction. So the particles of the solute, they interact wherever they are. They interact locally with their surrounding, and the surrounding is composed of molecules of the solvent. Yeah? And they feel some effective potential generated by the surrounding solvent. So we have to take that into account as well. Yeah? There will be some local interaction with the solvent, which is described by a local Hamiltonian. This local Hamiltonian contains a local potential, and this potential in turn may depend generally on the temperature of the solvent and may also depend on the density of the solvent. The denser the solvent, the closer the molecules of the surrounding solvent are to the particle of the solute, and that affects the potential that the solute, the particle, feels. For this reason, the local Hamiltonian may depend on temperature and density of the solvent. Now let's write down the grand canonical partition function for the full solution. Yeah, so for the solvent and solute together, for the entire system, or its log. It will depend on the inverse temperature of this dilute solution. It will depend on the Lagrange parameter alpha associated with the solute. because we have a mixture. We have two types of particles here. We have the particles of the solute, and we have the particles of the solvent. So when we characterize the system, we have two different particle numbers involved. And correspondingly, we have two different Lagrange parameters involved, associated Lagrange parameters alpha. And let me call alpha the Lagrange parameter associated with the particle number of the solute, and alpha primed the Lagrange parameter associated with the particle number of the solvent. And then it depends on volume. Now we treat solvent and solute independently. There's a factorization. In particular, the solvent is, and the thermodynamic properties of the solvent are unaffected by the presence of the solute. The partition function factorizes, and the log of the partition function is just the sum of the logs. So we have the grand canonical partition function of the solvent, which depends on beta. It depends on the Lagrange parameter alpha prime relating to the solvent and volume. This is relates to the solvent, and it's unaffected by the presence of the solute. So it's the same partition function that we would use if we didn't have a solute. This is a good approximation only if the solution is dilute, if there's not too much solute in the solution. And then we have the grand canonical partition function of the solute. But for the solute, we now have to pay attention that we have these two different kinds of degrees of freedom. We have the translational degrees of freedom, and as far as the translational degrees of freedom are concerned, we treat the solute as a classical ideal gas, monatomic gas, structureless gas. So if it was only the translational degrees of freedom, we would then have the log of the grand canonical partition function of a classical monatomic perfect gas, and this partition function depends on beta, it depends on the alpha relating to the solute, and it depends on volume. So if it was only the translational degrees of freedom, that would be it. But we also have this local interaction with the solvent. So the particles of the solute locally, they are sitting in an effective potential generated by the surrounding molecules of the solvent. And the dynamics inside this potential, this is in internal dynamics. So we do have, in this sense, internal degrees of freedom. And we learned that we have to take into account internal degrees of freedom by multiplying the log of the partition function of a monatomic gas with the partition function, with the internal partition function. So we have a prefactor here for the solute, and let me call the prefactor, the internal partition function, let me call that zeta. And that takes into account the local potential generated by the surrounding solvent molecules. This internal partition function may depend on thermodynamic variables, because we said the effective local potential generated by the molecules of the solvent may depend on the temperature of the solvent and may depend on the density of the solvent. Well, it depends, the internal partition function depends on beta anyway, because you have the trace over e to the minus beta times the local Hamiltonian, so there's a dependence on beta anyway. Here it may be a somewhat more complex dependence because the internal Hamiltonian itself may depend on beta. So you have, in any case, you have this dependence on beta. But then you also have the dependence on density. And one way of accounting for that is to allow for a dependency also on alpha primed. That's the Lagrange parameter associated with the particle number of the solvent. If the solvent is homogeneous, then the Gibbs-Duhem relation holds. And it says that out of 3 intensive variables, only 2 are independent. Now, if you consider as 3 independent variables the temperature, the alpha primed, and the density, which is also intensive, you can say you can always express one of them as a function of the other 2. So in particular, you can always express the density as a function of beta and alpha primed. So if there was a dependency on density, you can always replace that by a dependency on beta and alpha primed. Yeah, so by Gibbs-Duhem, we can account for the dependency, the possible dependency on density, by including the alpha primed here as a variable. Okay, and all of this takes into account here the local interaction part for the solute. Let's now look at some consequences of this form. One aspect that we can consider is that we look at the number of dissolved particles. So the number of particles of the solute. By our general framework, we obtain that particle number by taking the partial derivative with respect to alpha. We said alpha relates to the solute, so partial with respect to alpha of the log of the grand canonical partition function, no? The full grand canonical partition function. The first term doesn't depend on alpha. It only depends on alpha primed. The second term has this prefactor zeta, and the zeta doesn't depend on alpha either. Only the log of the partition function of the monatomic gas, only that part depends on alpha. So we have the zeta that remains unchanged, and then we have the partial with respect to alpha of the log grand canonical partition function of the monatomic gas with variables beta, alpha, and v. In the classical limit, we said we treat this approximately as a classical ideal gas. In the classical limit, the log of the grand canonical partition function is proportional to e to the alpha. And this means when we take the derivative with respect to alpha, we just reproduce the e to the alpha. So we just get, once again, the log of the grand canonical partition function. So, in other words, this is equal to zeta of beta and alpha prime times the log of the partition function of a monatomic gas. So here you see a difference to the monatomic gas classically. If you have a classical gas of structureless particles, for that case we had shown earlier that the particle number is simply equal to the log of the grand canonical partition function. Here this is no longer the case. Here you have a prefactor, and the prefactor is this zeta. We can now consider the pressure in such a dilute solution. The pressure, by our general framework, is always given by 1 over beta, and then the partial with respect to volume of the log of the grand canonical partition function of the entire system. So solvent plus solute. We can use the result from the previous page and find that this is, first of all, the partial with respect to volume of the log of the grand canonical partition function of the solvent only. This gives the pressure of the pure solvent. And we never cared what exactly the form is of the grand canonical partition function of the solvent. It can be whatever it is. Right? If it's a liquid, if it's water, then it's going to be different from the partition function of a gas, because a liquid has very different properties, but we don't care about the details. All we can say is that when we look at the pressure, we get here, the first contribution is just the pressure of the solvent. And it's the pure solvent, it's unaffected by the presence of the solute. And then we have the contribution from the solute. Remember, there's this prefactor zeta. That prefactor doesn't depend on volume, and therefore it remains unchanged when we take the derivative with respect to volume. So we still have this prefactor zeta. And then we have the partial with respect to volume of the log of the partition function of a monatomic ideal gas, classical ideal gas. Now this log of the partition function is proportional to volume. So as we have seen many times, taking the derivative with respect to volume is equivalent to dividing by volume. And then we still have the 1 over beta. But we learned on the previous page that zeta times the log of the partition function of the monatomic gas, that this is equal to the number of particles of the solute. And therefore, we just have a contribution to the pressure, which is n over beta volume, or expressed in terms of temperature, it's nkt divided by volume. This is the pressure of the solute. And it's the same pressure that we have in a classical ideal gas. So from the solute, you have a contribution to the pressure as if the particles in the solute constituted a perfect classical gas. And this is quite an interesting result, because despite the possibly complex interaction that you may have between the particles of the solute and the surrounding molecules of the solvent, as regards the pressure, you can still treat the solute like an ideal gas. So all the complexities of all the possible complexities of the interaction of the solute with the solvent don't affect the pressure contribution of the solute. This result can help explain effects like osmotic pressure. It can help explain the so-called Henry's law, which makes a statement about equilibrium between a solution with a dissolved gas and the same kind of gas above it, and other results that can be explained with the help of this result, that the contribution of the solute to pressure can simply be modeled as a perfect ideal gas.